Okay, so welcome to Dynamic Polymorphism with Code Injection and Metaclasses. My name is Sai. I'm at Tartan Llama on Twitter, and I work at Microsoft as their C++ developer advocate. You can ask me about that later if you would like. Usually when I say that, people have no idea what I'm talking about, which is fun. So before I get started, let's define what I mean by dynamic polymorphism. A kind of textbook definition of polymorphism is the provision of a single interface to entities of different types. And the key split which we're interested in for this talk is split between dynamic and static polymorphism. We're focusing on dynamic, where dynamic polymorphism is a runtime and static polymorphism is a compile time. Dynamic polymorphism gives you different behavior based on the dynamic type of an object, whereas static is the static type. Dynamic polymorphism in C++ is typically implemented with inheritance, whereas static polymorphism is typically with overloading and templates. Now, Louis Dion, a few years back, gave a really fantastic talk on runtime polymorphism in C++, where he gave a lot of examples of like why inheritance and the current ways which we look at runtime polymorphism in C++ have a lot of issues. Here's some of the things he says. Well, he says to listen to Sean Perrin, and sure, we can go back, and Sean has a bunch of fantastic talks all the way back to this talk, which was almost 10 years ago now. Inheritance is the base class of evil. Now, I'm not going to cover all of the things which Sean covers in his many talks on this topic, or Louis covers in his. If you'd like more details on problems with inheritance, please go back and watch those talks, but I will cover them briefly now so that you've got a basic understanding of what problems I'm trying to solve here. Now, one problem with inheritance is that it often requires dynamic allocation. If we have a base and then a few types which derive from base, then we can't have a function which returns base by value without slicing off the object. Like we can't return an A from this make base function or return a B. It's going to be sliced. Similarly, we can't have a stood vector of base and expect to be able to store A and B objects into this vector. Again, they're going to be sliced. Only the base part of the object is going to be preserved. So what we usually do is something like return a unique pointer or store a unique pointer. And this has a bunch of knock-on effects, which we'll see in a minute. But here I'm saying that we're having to use dynamic allocation in order to return and store these types. And as we'll see later, maybe we don't need to. Another is that we have pointers. As soon as we have pointers, we have considerations about ownership and nullability. And we can solve some of these with using things like null pointer, unique pointer, or shared pointer, or any of the other smart pointer types, or even just like decorator pointer types. But it's something we have to think about. It's also intrusive in that inheritance requires modifying the child classes. An example of this is, say I have a base class with a doThing function, which is in my library somewhere. And then I have another library, which I might get off in the ether from some third party. And that has some type which fulfills this interface. It has a doThing function, which is virtual and takes no arguments and returns void. I cannot dynamically allocate an instance of otherlibx and store it as a pointer to my lib base because x does not derive from base. This would work if we made x derive from base, but maybe we can't do that. Maybe we don't own this other library. Maybe we have to write a bunch of wrapper types and things like that. And if you've ever had to do this for a bunch of different types and maintain it, it can become a nightmare quite fast. So that's intrusivity. We also lose our value semantics, because we're, again, using pointers, knock-on effects, no more value semantics. We cannot just copy a unique pointer. It won't compile. We could implement something on top of this with what you might see referred to as a virtual clone idiom, where you have a virtual function which does a copy, preserving the actual derived type of the object, but it's more work we need to do. We don't have value semantics by default. And also this changes semantics for algorithms and containers. Like if you have a std set or something like that, because we have a pointer, the set is based on the pointer, not the underlying type. So this changes our semantics. These are all mostly knock-on effects of using pointers for our types because we want them to be polymorphic. Now, for the rest of the talk, we're going to try and solve these problems with inheritance, and we're going to solve them using some upcoming techniques in C++. Now, this is what I want to solve. This is my virtual version of some class hierarchy. Like I have an animal class, which has a virtual destructor, because if we have polymorphic objects, we usually want a virtual destructor, and a single virtual speak function. And then cat and dog inherit from animal, and they override this speak, and cat says meow and dog says woof, whatever. Now, what the kind of interface that I want will be different from this, but before that, we'll talk a bit about how this is implemented under the covers. So if we have a Felix object, which is going to be a cat, then this is going to point into a virtual table, a V table. And then this V table is going to point to the actual function for the cat object. So there's a couple of indirections here. This is how virtual functions are implemented. If we want to call speak, we indirect through the virtual table, and we indirect through a pointer to the speak function. Now, what I want is something like this. I want an animal class, which has some magic, which we'll define as we go along. And then I just want a cat class, a dog class, and speak functions. There's no virtual here. There's no inheritance. We're going to solve a lot of the problems we had with inheritance with this kind of model. And this will be our use case. We can create an animal from a cat and call speak. It will call the right function. This initialization of animal from a cat is not going to do any slicing. It's going to preserve the dynamic type of the object, but we're still going to call the right function. And similarly, we can create an animal from a dog and call the right function. It will all work. The magic is the interesting part here and what we're going to focus on. Okay, so to start, I'm going to implement this all by hand using C++ that you could write today. And then we're going to generate this stuff automatically using some interesting upcoming techniques. This is the kind of algorithm I'm going to use. First, I'm going to declare what a virtual table looks like for an animal. Then I'm going to define what the virtual table for a concrete type like cat or dog looks like. Then I'm going to make sure that we capture the virtual table pointer to our correct type, cat or the dog, when we construct our animal. And finally, when you call something on an animal type, we're going to forward calls through the virtual table. All right. This is how it looks. This is our virtual version. And we're going to declare the V table for, remember, we have this speak and we have this virtual destructor. So that's what our V table is going to look like. We're going to have a function pointer for speak and a function pointer for destroy. And these are going to take a void pointer. That's an implementation detail. You'll see how this works later. But this is what our V table looks like. It's just two function pointers for now. Now we define what a V table looks like for a concrete type. I'm going to use a variable template here. And it's going to look like this. We're going to have a function which calls speak for a given concrete type. This is the template. And we're going to have a function which deletes the object. And we can quite nicely define these using lambdas. So our first function takes a void pointer, casts it into our concrete type, and calls speak. Similarly, our destructor is going to cast to the concrete type and then call delete. All right. So this is filling in our vtable, which we declared here. And this is defining it for a given concrete type. This is usually called type erasure. Like we're capturing the concrete type in these lambdas and erasing it. So now here's how we actually do that capturing. We have our animal type, which is going to store a void pointer to our concrete type. And then we have a pointer to our vtable. Now in our constructor for an animal, we're going to dynamically allocate a copy of the t which were passed in. And then we're going to capture a pointer to the vtable for that type. All right, again, if you have any questions about this stuff, just drop it in chat or the Q&A. Finally, we're going to forward these calls to the vtable. So when you call speak on our animal, it's going to grab our vtable, and we're going to call the speak function pointer using our captured void star, which is our t underscore. And then when we destruct the animal, we're going to destroy it using the vtable. Okay. So now, if we have a cat and a dog, then we have this interface. We can create an animal from a cat, call speak on it. We can create an animal from a dog and call speak on it. I've got a question here. Can we use a smart pointer instead of void star, or are there reasons not to? Well, we're managing the lifetime ourselves because we have this destructor and we're having to call the vtable. We're having to call through the vtable to destroy the object. So we could abstract some of this into our own kind of void point, our own kind of smart pointer, but this is the behavior we're aiming for. And can I show again the t underscore definition? That is, sorry, that t underscore should be concrete underscore, but it's right here. It's the void star, which we create a copy of our constructor argument from. All right, any other questions before I move on from this bit? It can be a little bit bizarre if you're not used to this kind of construct. All right, not seeing anything in chat, so I'm going to move on. Oh, can you have a vector of animal? Not yet, soon. So let's look at those problems that we had with inheritance. We still have the problem of dynamic allocation. The dynamic allocation is now under the covers, but it's still there. But we have solved the problem of ownership and nullability considerations because we no longer externalize that pointer. We have an animal object. It's not a pointer to an animal, it's an animal. And we also got rid of the problem of intrusivity. We did not need to derive cat or dog from our animal type. It all just worked. So we've solved those two problems. We still don't have our value semantics, but we can get them. If we just extend our vtable a little bit, give it a clone function pointer and a move clone, and these are going to do broadly what you expect. The clone is going to create a copy, dynamically allocated. The move clone is going to dynamically allocate, but move from the object. And I'll briefly show you the definition. It's kind of messy, but it does mostly what you would expect. Those first two lambdas are the same as we had before. The next two, dynamically allocate and copy, or dynamically allocate and move. All right, so how we do the next bit is in our copy constructor for an animal and our move constructors, we forward through the vtable in order to copy or move the correct underlying type. And we also copy the vtable over from the other object. All right, so we're manually managing these vtables, and we've created our vtable by hand. And now we can create an animal, initialize it with a cat, call speak, And then we can overwrite it with a dog and call speak, and this will all do the right thing. And we can copy A into a new animal, and it'll all work. The V table will be propagated. We're going to capture the right types. It's all going to be magic. And now, like the question in chat said, we can have a vector of animals because we can copy these things and move them. All right. So we could create a vector of animals, add cats, dogs, fish, whatever, and then just loop over them and call speak, and it'll do the right thing. So this has fixed our value semantic problem. It's also fixed our semantics for algorithms and containers, so long as you go on and implement the necessary things that you might need on our animal type. You know, you might need to specialize like std hash for animal, add comparison operators, things like that. But that's doable, okay? We still have this problem of dynamic allocation. I'm not going to solve that right now. We'll get back to it later in the talk. But we have a new problem. Now we have to write all of this code. And it's not simple code. We're capturing virtual function pointers from lambdas. We're doing a bunch of things which you might not be used to in everyday code. We have our own custom destructors. You don't want to write this more than once, or even once, really. So we want to try and automate that. And this is what the key of this talk is going to be, trying to automate some of this. Now, as an aside, we need to equip ourselves with the tools such that we can actually automate this. And one of those tools is static reflection. Now, reflection is the ability of a program to introspect its own structure. And given that, static reflection is the ability to do this at compile time. Now, C++ already has a bunch of static reflection capabilities, mostly in the type traits header. So things like std is array. This is a reflection, right? You give it a type, it tells you if this type is an array. It's an introspection at compile time. Similarly, is same tells you if two types are the same. You're asking questions about your code and the structure of your types at compile time. But it is limited. You know, how about taking an enumerator and getting a string representation of it, or iterating over the members of our types? We can't do this without building something additional on top of it. And you know, there are a bunch of tools which do this, and usually you will use macros or some external code generation tool or something like that. Static reflection builds this into C++ as a language. So this is the paper, which is the kind of direction which C++ static reflection is going in. It's called scalable reflection. I'll give you a kind of brief overview of what utilities this provides. Now, this enumerator to string, which was an example I just said, is something which pops up so often, and it's such a pain. Like every single time you have an enumerator, and you're like, oh, I need to translate this to a string. Now I need to, either do a bunch of macro nonsense or just write this code by hand, or it's just a pain. I'm sure most of you have had to deal with this at some point. So what we can do with scalable reflection is something like this. Now, this is a for const expr, not a normal for. It's equivalent, it's a for loop, but these the thing it's operating on might be of different types. So it's operating at compile time. So what we're looping over is a representation of all the members of our enumerator. So if our enum is color, then this would operate over red, yellow, green, so on. Now, part of the magic here is this reflexper operator. This takes in some entity and gives us back a representation of reflection information. And then this members of will take that representation and give us something which represents all of its members, which we can loop over, which we can ask questions about at compile time. So then we can do something like ask if our the given value that we have to our toString function is the same as this entity, if it's red or green or yellow. And if it is, this expr ID is called a reifier. That's the opposite of reflection. Reflection takes some C++ entity and gives you back information about it. A reifier takes that information and turns it back into some C++ entity. So if the value is the same as the thing we're looping over, then we're going to return the name of it, returning red or yellow. And otherwise, because enum, the enumerators, you can have an unnamed enumerator in C++, like something which is outside the range of the named enumerators that's valid. So we're going to handle that as well. And now this will work for any enumerator. We don't have to write our macros or do it by hand again. It's pretty nice. What is the type of E? The type of E is a std meta info, which is a type which represents reflection information. So I mentioned reifiers, that expr ID was a reifier. So another question, are there any benefits of declaring toString as const expr? Yeah, you might have an enum, which is, you might have an enumerator which at compile time, and you might want to use the name of that to generate some strings at compile time, or to use in compiler errors, even given some of the facilities I'm going to be talking about later. So that, yeah, there are times that you might want to do this at compile time. So that expr ID was a reifier. I'll just briefly go over the reifiers. I don't want this to get to, just going over all the details of this paper. If you want more information about reifiers and reflection, I'd recommend going to Andrew Sutton's talk, which I believe is later today. And I think he's going to go over all of these things in more detail with more examples. But the reifiers which the paper gives us is you can turn a reflection into a type, you can turn a reflection into a namespace, into a template. And if a reflection represents a value, like if you take a reflection of the literal 4, then I mean the number 4, 5, that would be a better example. Like if you take the reflection of the integer literal 5, then you could get the value of it back in the C++ world. expr ID is the one we just saw. And then we have this kind of weird syntax, which can also be spelled unqual ID for turning a reflection into an identifier. And the interesting thing about unqual ID is you can also generate new names. Like if I have an entity whose name is X, I could generate an identifier which has a given prefix or suffix, which will be very, very useful later on. And then a similar thing for template arguments is templarg. All right, code injection. If you have any more questions about reflection, please drop them in Q&A or chat. But I'm going to move on to code injection. Say we have a point class with just 2 members, X and Y. Now, this is an example of getters. I'm not saying to use getter functions in your code. People understand getters, which is why I'm going to use this. But say you want to have getter functions for X and Y. This code is pretty repetitive. We have our int X, we have our int Y, and then our get X and our get Y are just returning them. It's kind of a mechanical translation. Before I move on to that, there is a question in chat asking if reflection is part of C++ 20. It's not. It's targeting C++ 23. So what if we could take our getter code and instead of writing this by hand, if we could just generate it automatically, if we could do something like this, say, generate getters and give it the reflection of our point class. And this would just generate exactly the same code which we've written by hand, but it would do it automatically. Now, one thing to note, this const eval block says, run this code, which is in this block at compile time. It's not const expert, it's const eval because it definitely is at compile time. And then this generate getters function is something we're going to write ourselves. So I'll show you what this is going to look like. Now we have our generate getters function. This is the meta info type, which I mentioned earlier, which represents the reflection information. And kind of similar to the enum example, we're going to iterate over our members. We're going to ask if our member is a non-static data member. And if it is, then we're going to generate a getter function for it. Then our generate getter function is going to look like this. Now, this is where the magic of code injection comes in. This arrow is an injection statement. And this fragment keyword says that I am a fragment of code which you can inject somewhere else. There are a bunch of different kinds of fragments you can have. You can have fragments which can be injected into classes, like this one, because it says fragment struct. Or you can have fragments which can be injected into namespaces, which is spelled fragment namespace, or just block fragments, which don't have struct or namespace after them. What this is going to do is when this code runs, it's going to inject some code into the scope we're currently running in, which, if we go back, is this const eval block. So this code is going to be injected into where this const eval block is. Now, what this code looks like is this. We want to generate something like this. A get x function, which returns an const reference and is const. Now, the way that I like to write injection code is start off with what I want to get for some example, which is this, and then try and translate it into generic code as we go along. So that's what I'm going to do here. So first, we don't want to just hard code our return type because our members might be ints, they might be floats, they might be some user-defined type, they could be anything. So we want to get this from our reflection information. And we do this like so. We say, give me the type of the member, and then reify this, turn it into a C++ type. Someone says it's not a million miles away from a macro, but for the 21st century. It's the difference between macros and this is in the C++ world. Like macros do not understand C++ types. They do not understand even things like template syntax. This is in C++ world that you can work with C++ types. You can manipulate them. Anything you can do in C++, like we're working in that world. Someone says, can you nest const eval blocks? I guess you could nest them at the top level. I don't know what that would do, but you can definitely nest them. Like if you have a const eval block and then you have a fragment which also has a const eval block, yeah, that can make sense. Someone says, just generating the getters via const eval block. Like via const eval work with IntelliSense and Visual Assist. This is very experimental work right now. So this kind of stuff is not built into IntelliSense or IDEs. And someone else says, is error reporting better than macros? You'll see some facilities for better error reporting later on in the talk. And someone says, let's also hope it will work with Oxygen. Yeah, that would be nice as well. Although I have opinions about auto-generated documentation. Someone said, how will this generated code interact with debugging? Yeah, that's an open tooling question. Like, how do you tool this kind of thing? There, you will see some facilities later for you can say to the compiler, print out what code you generated from this so that I can look at it. So you can imagine that could be built into your IDE. Like you could hover over some type and it would give you like the code which is actually generated by the code injection, things like that. So this is like if you think about it, you can trivially come up with ideas for how tooling could help. And that will be an open question moving forward. But to come back to this, this transformation. So instead of int hard-coded, I want to get the return type from my member. So I get the type of the member and turn it into a C++ type with this type name, reifier. Then I don't want to hard-code get X. I want it to be get underscore whatever the name of my member was. So I can do that using unqual ID. This is using unqual ID with a prefix. I want unqual ID can take any number of strings, of string literals or any compile time strings, and turn it into a single identifier. So this will give you get X or get Y or get foo, get whatever. And then we want to, in the body of this, return the member itself, X or Y. Question is, as we inject this fragment into a struct, which access specifier is used? The one from the place where we inject? No, the one from, so here I'm using the struct keyword, which means it'll be public. If I used class, it will be private. You could also put a public or private specifier inside this fragment block, and that will change the access specifier. Oh, someone says, what is the percent sign syntax? So this is something which has been changing recently in the experimental implementations. It used to be that you could just say, give me the type of member here, and it would all just work. But now we're moving to a model where you have to explicitly say, member is something from outside the scope of this fragment. So I'm referencing, imagine if this was a lambda, and if you captured something, imagine you had to decorate that inside your lambda. This is the same kind of thing. You're saying I'm referencing something outside of this block, and that tells the compiler it needs to do some additional magic. Someone asks, why do we need an additional set of brackets after unqual ID? Because this is a function which takes no arguments. So this unqual ID will collapse down to a single identifier, like get X, and then those parentheses say that this is a function which takes no arguments. Someone says, can we toggle whether we want to refer a copy or a reference depending on the member type? Sure, you could do anything here. You could do ridiculous metaprogramming stuff. You could, anything you want. And someone says type of, and then the percent sign member feels like it could have been member.getType. You could argue syntax here. You would still need to do the percent sign braces because you're referring to something outside the scope of the fragment. Someone else says, can you also do string manipulation? I haven't tried doing that, but in theory, sure. You can do any kind of manipulations you want here. Okay, so feel free to keep those questions coming, but I'm gonna move on a bit. So this is the code we had. We call generate getters, and then it injects the code into this scope. It's pretty cool, I think. We're going to see more powerful ways of using this pretty soon. So code injection and dynamic polymorphism. How do we put this all together? How do we take what I did at the start of the talk, where I implemented all of the essentially inheritance and virtual function mechanisms by hand and got something better than inheritance, but how do I automate that with code injection so that I don't have to write all of that by hand? And this is what our animal type looked like. We had our concrete void star, we had our vtable, which we capture, and then we had all of our constructors, forwarding functions, and things like that. We're going to generate all of those constructors, forwarding functions, all the magic automatically. So the first thing we do is we're going to transform our animal into a template. So this is what we had before. It's an animal type because this is for a specific kind of inheritance hierarchy. You can think of it as, we're emulating a particular virtual function interface. But we want to be able to use this for anything, so we make a template. We're going to call it type class 4. So just a name I picked because it's kind of like Haskell type classes. And then our template argument is called a facade. That's what I'm calling a facade anyway. So our facade for an animal will look like this. It's just a type which has a function declaration. This function declaration will never be defined. It's just there to give us information about our interface, all right? So this animal facade, you would pass this as the template parameter, and it will generate you all of the necessary code. Kind of like this. So previously we hand wrote all of our animal code. With this model, all we do is write a facade, which specifies our interface, and then we say that our animal type is the type class for our given facade, which is just a single speak function. And that will generate our virtual destructor, our speak function, our forwarding functions, our copy constructors, our move constructors, doing everything we already did. Okay, so we're going to follow exactly the same algorithm we did at the start of the talk, but instead of writing by hand, get the compiler to write it for us. So the first thing is declaring the vtable. Now, if you remember, this is what our vtable looked like. We had our speak function and then destroy, clone, and move clone. Now, the last three are going to be the same no matter what your facade is. It's only the top one which is going to change, or you might have more than one. Someone's asking if metaclasses would make this even better. I'm going to speak about that at the end, yeah. So let's focus on this speak function because that's the thing which is going to change depending on your facade. So now we're going to make our vtable templated on the facade. And we're going to have a const eval block. Now this for each declared function, this is just some helper I wrote, which will loop over all of the declared functions in our facade and call this callback with the function reflection, the return type, and the parameters. The implementation of this is not very interesting. It cleans up the code a lot. So now what we want to do is for every declared function in our facade, we want to inject a function pointer type into our class definition. And for speak, it will look like this. Returns void, it's a pointer to a function taking a void pointer, and it's called speak. Now, similarly to what I did earlier, I'm going to transform this into a generic version as we go. So our void type, that's going to be the return type of the function. It could be, with speak is returning void, but maybe it's get number of feet, and that's going to return an int. So we need to change this depending on the return type of the function in our facade. Similarly, the name, we want the name to be the same, so we just use unqual ID. And then if the function takes any additional parameters, speak didn't take any parameters, but maybe some other functions of an animal would take parameters. So we inject those into our parameter list. Someone asks if there are a way to print out the code generated for type class 4. Yes, there are some facilities to print out the generated code in the experimental implementation I've been using. But this is our vtable now. We're generating a bunch of function pointer types automatically based on the facade. All right. Now we're are there any questions about this? Because it's, this stuff can be kind of weird and new. But essentially here for our animal type, this is defining our speak function pointer. but this is going to be done for every single function in your facade. So I'm asking, where does pointer come from? This pointer is going to be provided by our forwarding functions. So when we define our forwarding functions, we're going to pass in that captured void pointer into our vtable. Okay, now we're going to define a vtable for a concrete type, like cat or dog. So this is what our it could look like beforehand. We would fill in our table.speak function with something which static casts to the concrete type and then call speak. So we want to, again, generate this based on our reflection information. So we're going to make a fragment. We're going to transform. We don't want speak anymore. We want this to be based on the function name from the facade. We want to inject any additional parameters, just like before. And we also want to return it in case the function returns any data. You know, speak didn't return anything, but get number of legs would. All right. Then we want to capture the vtable pointers on construction, which looks pretty much identical to what it did before. You know, now that we have our type class 4, which has our vtable and our concrete type, then we do the same as before. We dynamically allocate a copy of the T and we capture the vtable pointer. The only thing which is different is there's some template parameters in here. Someone's saying that the generic transformation obscures the structural cues. Yes, you do kind of get used to it a little bit, but this is the same with any kind of generic code, right? Like because in C++ you have to focus on so many different details when you're writing generic code, some more like abstract things about the structure get a little bit lost. So it's something you get used to as you write more code like this. And then finally, we want to forward our calls through the vtable. And I'm not going to go through this transformation. I don't want to spend too much time on this code, but it's the same kind of thing. We're just taking our the final version we want, and we're changing it into something which generates it based on the reflection information. So now we've gone from all of this code, which is what I hand wrote at the start of the talk, and this is exactly the same. This now generates all that code at compile time without us having to write anything extra, which I think is really cool. Are we presently missing the copy move functions? That's going to be the same as the start of the talk, right? Like the, here we're doing the capture of the vtable pointer, and then underneath here you would have the copy constructor and the move constructor, and those are going to be the same for any type, as long as you actually want those copy and move constructors. And there are ways that you could customize this, but that's going to be exactly the same. I just didn't write that code in here because it will be exactly the same as the handwritten stuff. And that will, again, go in our type class 4 implementation, which we write once, rather than duplicating it for every single like animal or vegetable or mineral, whatever type class we're writing. Okay. So another thing we can do is, I said we're going to try and fix that dynamic allocation problem, and we haven't done that yet. Oh, my light just fell over, so I'm going to go stick that back up. So what we can do, in addition to, now that we're in a kind of generic world, we're taking template parameters, we can do a lot of cool stuff here. Oh, so, yeah, someone's just saying that the concrete type's still allocated on the heap. Yeah, getting to that right now. So what we could take is a storage policy. And this storage policy would say how to store the concrete object. Currently we're dynamically allocating it. but we could do something different. And similarly, we might have a policy for storing the vtable. And this might allow us to do things like, previously we were saying that we have a type class for an animal facade. Well, maybe that's the same as saying that I want a type class for an animal facade. I want remote storage, i.e. always dynamically allocate my stored object. And I want a remote vtable, i.e. store a pointer to the vtable and store the vtable in some static storage. Right? That could be the same thing. But then I could customize this. Maybe I want to use a small buffer optimization. So I could say, instead of use remote storage, use a small buffer optimization with a buffer of size 32 bytes. And now if I create an animal with some object which is 32 bytes or smaller, then that's going to go in my static storage. And otherwise it's going to be allocated on the heap. And I could say, store the vtable in place. So, if I have a small vtable, like, for animal, our vtable was only a single pointer. So if we're wanting to call speak, usually in a virtual function, we're having to indirect through the vtable and then through another pointer. Well, with this, we could just store the single pointer in place. And every animal object would just have a pointer to speak. And maybe this makes sense, if your vtable is just a few functions in size. Maybe you just want to store all of those functions inside the object. Maybe that makes sense. And someone says that's going to help with compile optimizations and prefetcher. Yeah, like as soon as we're avoiding allocations and pointers, this stuff really helps caching and all that stuff, which can just magically make your performance so much better. And then we could go even further. We could say, actually, I want to never dynamically allocate. I want to only use in-place storage. And if you try and create an animal from something which is larger than some maximum or whatever, then throw a compiler error. And you could even split the vtable. Like maybe your speak function is called like all the time in your code, and you don't want to do two indirections for that. Well, maybe you could store that inside the objects, and then you could store a pointer to the rest of the vtable. Like this is possible. You can do anything. It's really, really flexible. Whereas with virtual functions, your compiler implementation, your ABI is going to specify how this is actually implemented. With this, you can do anything. So back to our problems with inheritance. Now we've solved that problem of requiring dynamic allocation when we might not want it. We're not having to allocate pointers unnecessarily. We can use SBO storage. We can use in-place storage. We have control, which we didn't have beforehand. So now this is what we ended up with. We could actually make this even better. Someone earlier mentioned in chat metaclasses. We could have something like this. We could say animal is a type class, and it has this speak function. This is what metaclasses give us. I'm going to talk about metaclasses now. If anyone has questions on this stuff, drop them in chat. All right, metaclasses. So this is a description from the metaclasses paper. Metaclass functions let programmers write a new kind of efficient abstraction, a user-defined named subset of classes that share common characteristics like user-defined rules or defaults, or in our case here, generated functions. Here's an example from the paper. So say we have a point class again. Presumably we might want to do things like compare this, or I don't know, have like a std get or whatever. Maybe we want to treat this as a value. We don't want to write all of those comparisons ourselves. Of course, with spaceship operator, we don't have to do that anyway. But for the sake of argument, maybe we don't want to write comparison operators, all of the stuff we would usually write to treat an object as a value. Maybe we want that generated ourselves. So we would say point is a value. And then in some library somewhere, we would have a function called value, which takes in reflection information and does a bunch of injection statements, injecting things like the comparison operators. And now metaclasses, it looks kind of like magic, but this part translates quite nicely to code we've already seen. So we have our point, which we're saying is a value metaclass. And what this translates to is we just copy the entire contents of the point class into some hidden namespace, into some prototype. And then we have our point class, and we just call the value function with reflection of the prototype that we've copied and the contents of the point class into. All right. So this is like the entirety of, not the entirety of, but it's a lot of the metaclasses proposal in just a single slide. Someone asks which paper is covering metaclasses. I'll link to it at the end. It's a different paper than the reflection one. And it's not targeting C++ 23, as far as I know. More like 26 or something. Someone's asking, can I have more than one metaclass? I can't remember. You could foresee an implementation which allows you to, have multiple metaclasses inside that class brackets, just separated with a comma, and then calls each function in turn. That could make sense. I can't remember if that's present in the proposal, but it's a possibility. Another example from the paper is, say you've decided that everything I've talked about in this talk is utter nonsense, and actually you love virtual functions and you want to use them everywhere. Well, if you have a shape class and it has a bunch of different virtual functions and then has a virtual destructor, and you need to be careful not to write any like non-public or non-virtual functions, because this is supposed to be like an interface type thing. And there's no enforcement of any of this. You're just kind of bound by your own rules. Maybe you would want to write something like this instead. Say that shape is an interface. And similar to what I've been talking about in this talk, you might just say, okay, here's what the functions look like. And you want these to all be pure virtual. You want a virtual destructor, all that stuff. And you want this to be, you want to get good compiler errors at the same time. So what it could look like is this. This is the implementation for the interface meta class. So first, it would do something like, we want to record whether someone has defined a destructor inside the interface. And then we're just going to loop over all of the member functions which are declared. Then we're going to use this compiler require thing, which is, earlier I mentioned that later you're going to see some ways of generating better compiler errors. Well, this is that. It's kind of like a static assert, but it's operating on reflection information. You're saying require that this thing is not a data member, because you don't want your interfaces to contain data, and you don't want them to have copy or remove constructors. Instead, you want to say like use a virtual clone. So these give you better compiler errors based on information known about your types at compile time. And then you would want to do something like make sure that everything is public, make sure make everything pure virtual, and keep track of whether a destructor has been defined or not. And then finally, you'd want to inject this new pure virtual version of the function into the scope of the class. And then finally, you would want to declare a virtual destructor. So this is the implementation of interface. You could go ahead and specify a compiler feature which does the same kind of thing and write a proposal to the C++ standards committee and probably have it rejected for it being too narrow. Or you could write some code as a library which you can ship and which you can test and which you can version. And it's kind of cool. You're writing your own abstractions. You're writing your own language features, essentially, but as a library. Someone's asking, can you experiment with this? I'll get to that in a bit. And similarly, our type class meta function would do exactly the same thing. Earlier I showed you that type class 4, which did all of the injection statements and things like that. Instead, you would just do that inside a type class, and it would give you the same thing. But now it would let you do something like this. You say, I have an animal, it's type class, it has a speak function, and then I can have a vector of them. And I have value semantics. I can control the allocation of the V table and the underlying object. I can do all the stuff you've just seen with like really, really terse syntax. And not only is it terse, it's clear as well. I'm saying animal is a type class. I'm defining my own abstraction and then using it in my code. So of course there are some concerns. Runtime performance is one. How does this actually compare to virtual functions? I did some micro benchmarks and things like that, but micro benchmarking something like this, which depends so much on cache behavior because things are allocated on the heap or the stack or whatever, is it can be so misleading. So I didn't want to include any hard numbers here, but you can see how this would affect performance. You can bring things closer to cache. You can avoid additional pointer leaps. All the kinds of things which we do as optimizations anyway. Now we have more control over than virtual functions, which are all implemented by our compiler. Another is compile time performance. Like how does something like metaclasses compare to, or code injection? How does this compare to doing like ridiculous quantities of meta programming combined with some code generation tools or macros? From what I hear from the EDG folks, they're seeing really good results because templates have issues like you have to do memoization, you have to instantiate large blocks of code and then keep them around in memory and things like that. This code injection turns out to be able to be implemented more efficiently, according to early experiments. So that's promising for me. An issue I have with this is that it's essentially a new and incompatible way of specifying concepts, right? Like the version of concepts which landed in C++ 20 is based on use cases, right? We say something is an animal if I can call a speak function on it, which is different from saying something's an animal if it declares a function called speak, which returns nothing and takes no arguments. You cannot generate a type class from a concept, at least not today, and it's unclear if it's possible in the general case. So that's a problem I do have. There's people who are looking into possible approaches to, how do we merge these concepts? How do we make sure that we don't have one version of concepts for compile time and one version for runtime? Some future work. There is a paper called PFA, which defines pretty similarly the kind of things I've talked about in in this talk. It takes a little bit of a different approach to some of the details, but it's broadly similar and can be implemented with the code injection and metaclasses approaches. Another paper, which is from this year by Barry Revson, is we need a language mechanism for customization points. This paper doesn't so much propose approaches for this. It looks at different approaches which are in the pipeline and compares them. I would definitely recommend going and reading this. It's kind of intended to generate discussion around these topics, and it talks about some of the issues I've talked about with different versions of concepts and things like that. Here are some links. So someone asked earlier if you can play around with this. There is a version of there is a compiler, experimental compiler made by the folks at Lock3, which has a Godbolt version. So you can go check it out on Compiler Explorer and play around. If you just go to godbolt.org or I think cppx.godbolt.org, you can play around with it. And the code for this talk is at this Godbolt link. I also made a prototype implementation, which takes a little bit of a different approach from what I talked about in this presentation, but it's a little bit better commented and maybe more understandable. You can check out the experimental Lock3 compiler at GitHub. It's a Clang fork. And so you can play around with it, send them issues. Oh, this is the Compiler Explorer link, cpp.x.godbolt.org. The scalable reflection paper is here, P1240, and the metaclasses paper is P0707. So thank you very much for listening. And I will now take any additional questions you have. So one question is compiler diagnostics for fragment injections. So from what I remember, if you'll get compiler diagnostics if you inject things into the wrong scope. Sometimes you will get unclear compiler diagnostics because, as I said, this is experimental work. It's still very much ongoing. If you play around with this stuff, you'll probably find compiler bugs or things which could be improved. But they will be improved and the compiler bugs will be fixed. So yeah, keep that in mind if you play around with this stuff. It's not perfect yet. Someone else says, how ugly are the error messages of the compiler if there is an error? Do you see debuggers can see through this and allow stepping through the metacode? So yeah, I think that it's an open tooling question. I can see many different ways you could implement something. Like if you, for example, if you had your animal type class and you had your dog and your speak function, then what kind of stack trace do you get if you break inside dog.speak? Maybe it would look something like your dog.speak function and the implementation, and then maybe the debugger could give you the code generated from the animal class so that you could look at it and step through it and things like that. The debugger would have to either communicate with the compiler. The compiler could, for example, for any code it generates, it could put the generated code into the debug information. And then the debugger can, show that, and you could potentially step through it and things like that. So there's lots of different ways you could implement something like this. And the compiler errors, again, there's a lot of work to be done there, but because the compiler errors would be more programmable, like people who are writing type metaclasses or code injection code could make their compiler errors better for users. Someone also says Sean Baxter's stuff is interesting too. Yes, definitely go check out the Circle compiler. It's essentially an extended version of C++, which has additional meta programming stuff built on top, and also has some really interesting shader functionality as well. Someone says, is it fair to say that the proposed polymorphism solution is C++ 11, ignoring code injection and reflection? I think the original code that I showed, you would need C++ 14. Did I use generic lambdas? Maybe it would be C++ 11. I mean, I'm sure you could implement it with C++ 11. And of course, people have done similar things with C++ 03. You just need a lot of macros and a lot of pain. Any other questions? Slides. I will put slides up on Google Slides or something. I'll link to them in Discord, and I'll tweet a link to them as well. I'm at Tartan Llama on Twitter. If you want to follow me there, I mostly post pictures of my cats and terrible jokes. But if there are no other questions, then thank you very much, and I hope you enjoy the rest of the conference.